So let's try it this way. We have already seen random events in which outcomes are clearly separate, and we call such random events discrete random events. So discrete random events has separate outcomes, and if I were going to illustrate those outcomes in some abstract way, maybe using the number line or coordinate plane, I will put dots, unconnected dots. So for example, here we have all of the outcomes for a coin toss. We have heads and we have tails. Or if we have two coins and we're tossing them at the same time, our outcomes will be 4 dots on this plane. So you can have two heads, which corresponds to this dot here, or one head and one tail, which are these two, or two tails. But the main thing is that those outcomes are separate. You cannot have something between heads and tails when you are tossing the coin. So you can't have half tails and half heads, which would correspond to this point. And you can't have quarter heads and 3/4 tails, and so on. So your outcomes for discrete events are separate, and there is nothing in between. There is another class of random events, or random variables. Oh, yes, random variables. And we call them uniform random variables. So I tried to use two different examples. Oh, sorry, it's not uniform, at least not yet. Continuous. So the next class will be continuous random events or continuous random variables. So let's see. One example I was starting is time of the random event, for example. So let's say you come to campus every day between 1 p.m. and 2 p.m. So can you come at 1:30, which is 1:30? Sure you can. Can you come at 1:15, which is 1.25? Again, you can. And you can even come at the moment that corresponds to something like 1.8734 and so on. So in fact, if I was going to illustrate the time at which you come, I cannot do it using separate dots. So in fact, to do that, I will have to paint the whole interval. So even if I used the dots, those dots would connect and fill the whole interval between 1 and 2 p.m. So let me just do it by shading that area. So that's all the possible outcomes for the time, random time of your coming to campus. All the points in between, all the numbers which are greater than or equal to 1 and less than or equal to 2. All of them are eligible. And how many such numbers are there? Well, we know the answer. There's infinitely many. You can't say that there are 100 numbers between 1 and 2, or that there are 1,000 numbers between 1 and 2, or that there are million numbers, and so on. There are infinitely many. That's one of the main properties of continuous random variables. They can acquire infinitely many different values. Well, we have already seen something like that. So if you look at Poisson distribution, there you can also have infinitely many different values for your variable. However, in case of Poisson distribution, they are countable. So if random variable x has a Poisson distribution here with some lambda, then your x can be equal to 0 or to 1 or 2 or 3 or 4 and so on and so on. Yeah, 10,000s. Okay, 1,000, 1,001 and so on. There are infinitely many of them, and they are countable. You can count them. You will not reach the end, yeah, never, because there are infinitely many numbers, but you can count. All of your life will be spent counting, but you can do that. In case of continuous variable, you cannot do that. So if we look at this example, yeah, when we have continuous variable spread between 1 and 2, there is no way to do something like this. So, for example, you can have exactly 1. What is the next number after 1? Well, if it was only integer numbers, I would put 2. But here we have all the numbers in between. And you can, for example, say, well, the next number is 1.1. But what about 1.05, for example, or 1.001 or 1.0001 and so on. So there's no way you can count all those possible outcomes, and that's how do I say it? So not only we have infinitely many outcomes for continuous events, but we have uncountable number of outcomes. So you can have infinitely many outcomes in discrete variable too, in discrete event too, but it will be countable. And this one, for continuous variable, it will be uncountable. So let's look at one more example. And this is your time when you come to the campus. What about your height, for example? So we know there are some loose, not exact boundaries for height of a human being, and let's focus on human beings which are about 20 years of age, or 18 or 22, so around that. And we can say that human beings around 20 years of age will have their height between 1.3 meters and all the way up to maybe 2.2 meters. So these numbers on the extremely low side, they are for midgets, Yeah, so there are people with some issues with their hormonal systems, and they won't grow properly, and they will have extremely short height, like 1.5 meters. And also there are whole populations which are just genetically short. So pygmy people of Africa, for example, or Andaman Islands, their heights are usually no more than 1.5 meters. So the lower boundary is that 1.3 meters, and upper boundary, well, I'm not totally sure about that 2.2. Maybe it's a bit higher. Maybe there are some people who are 2 meters and 40 centimeters, for example. But let's for now assume that the higher boundary is 2.2, and that's the only two exact points, only two exact values. And the height can be anything in between. So for example, your height can be 1.72 meters, or it can be 1.72578, and of course you can say, well, look, who will be interested in measuring the height up to the millimeters or the fractions of millimeter? And the answer will be, of course, no one. Yeah, so usually when you ask about height of a person, we answer in meters and centimeters. We won't go further than centimeters. So for example, my height ranges somewhere between 0.76 meters and 0.78 meters, and that depends on a lot of factors, like when I'm full of energy and slept well and so on, my height is this. And at the end of the day, when I'm tired and stressed and distressed and so on, my height is like this. And that's because those discs between the sections of your spine, they expand or retract based on your physical well-being. So your height can change for about 2 or 3 centimeters this way or another. But that's not the point. You will never see someone say that his height is 1 meter 76 centimeters 3 millimeters. But still, those differences are there. So we might be not interested in millimeters, but if you take two people who are both 1.70 meters in height, in fact, their height is not completely same. There are differences in millimeters or in fractions of millimeters. So your height can be any number between 1.3 and 2.2. So there are infinitely many different possible heights of a human being of 20 years of age, right? By the way, the same applies here in case of time. So nobody is interested in the exact second when you come to the campus. Even usually the exact minutes are not interesting, are not relevant. So if somebody asks you when you come to the campus today, you will most probably answer, well, I will be there at 20 past 1, right? And on almost no occasion you will say that you will come to campus at 1:27 and maybe 32 seconds. But still those differences are there. So that's our continuous variables. And those continuous variables pose a threat to our definition of probability. So for now let's remember the definition of probability we used at the start of our course, and we used it for discrete random events. So to find the probability, we take the number of favorable outcomes, and favorable here just means those outcomes for which we want to calculate probability. So we take that number of favorable outcomes. I want to write the word outcomes. I'll leave it as this, number of favorable outcomes, and we divide it by total number of outcomes. And that's where our definition cracks. So if we use this definition, then what's the probability that you come to the campus exactly at 1:30, given that you come there between 1 and 2 p.m.? Well, there is only one moment in time, there is only one moment in that interval between 1 and 2 when time is 1.30. So number of favorable outcomes is 1. And total number, as we already said, is infinity. And we cannot calculate that. Infinity is not a number. You can't divide by infinity. Of course, you can do something like that. You can calculate some 1 over some n, and you can find the limit when n tends to infinity. And if you remember your calculus, then you will know that that limit is 0. So probability is 0. But again, usually when we say that probability of something is 0, it means that it's impossible. Event with probability of 0 never happens. But here we have an event that could happen, and that happens pretty much every time, but the probability is 0. So what is it telling us? It's telling us that either something's wrong with the definition of probability we are using, or something is wrong with the concept of probability itself. So we need to fix that. So we have to either change the definition, or we have to find another concept which will still show us the likelihood of the event, but which won't be the same as the probability. Well, let's try. We can do. So first thing I want to do is I want to turn my continuous event into some kind of discrete event. So let it be 1 p.m. and let this be 2 p.m. and I want to divide that time interval into several parts. So maybe, just maybe, I'll take this one, which is 1:20, and then I will take this one, which is 1:30. So now we have 3 intervals of different length, and those are time intervals. So first of them is 20 minutes long, and the second one is 10 minutes long, and the next one is 30 minutes long. Okay, let's call them A, B, and C. It doesn't matter, in fact. Those are just the arbitrary names. So let's call them A, B, and C. Well, now I can do something like this. I can say, what's the probability that you come to campus in the interval A? So I can find that probability, right? But instead of counting the number of outcomes, I will do something different. So if I count the number of outcomes, then I will have infinitely many points here inside A. And I will have infinitely many points here inside the whole interval between 1 p.m. and 2 p.m. And I will have to divide infinity by infinity. But again, we cannot do that. However, intuitively, we understand that those two infinities are different infinities. They are not the same. So one of them is larger infinity, if I say so. And one way to measure how large that infinity is would be taking the length of the interval. So I take the length of this interval, length of interval A, and it's 20 minutes. And then I take the total length, which is 60 minutes, 1 hour. And that I can calculate. That's just 1 over 3. We have our probability. And we can do the same with B. And we will have 1 over 6 for probability of B, because 10 minutes over 60 minutes. And then for C, we will have 1 over 30. So we still can calculate probabilities, but not for separate points. We can calculate probabilities for intervals. Okay? So now let's look at that more closely. So again, let's assume that our interval starts at some point A and ends at some point B. Yeah, in previous example it was 1 p.m. and 2 p.m. But now for generality, let's just say that it's A and B. And let's say we want to find probability for our random value being between these two values, which I will denote by x1 and x2. So the length of this interval is x2 minus x1, and length of the whole segment is b minus a. So this is our probability. And if I want to find probability for this interval between, say, y1 and y2, then it will be y2 minus y1 over b minus a. So you can see there are similarities. First of all, both of those probabilities depend on the coordinates of the starting point of our interval and end point of the interval. And both of them have this common denominator. So in a more generalized way, I can write something like this. So we have some f times x2 minus x1, right? And this f in our case is just 1 over b minus a. And now I want to call Okay, not call. So, okay, let's do this. So, again, if you remember the calculus, there is a thing called, well, derivative, and now we will use that derivative. But first, let me do this. So, I introduce a new probability. So, in those examples we have seen, we were taking the arbitrary intervals between inside our segment. Now I will introduce the new thing. So I choose only one point on the interval, let it be this, for example, and I want to find the probability that my variable will be in the part of the segment which is to the left of x. So in this part, starting with a and ending with x, and I will call that probability p over x, right? So here it's x minus a over b minus a. It depends on x, it's the function of x. So we can take the probability. So most probably, oh, we can take the derivative, sorry. Most probably you noted the derivative by a prime, or maybe by this, dp over dx. So anyway, whatever you did, you will get your 1 over a, sorry, it's not a, b minus a. And now I will say, wait, well, here it's the special case, probability is same everywhere, likelihood is same everywhere, and that's why we get this number. It's a constant number because your b and a will never change, but in total, derivative of the probability on x can be a function of x, and we call that function density. So it's a density of probability. So probability density. In our previous examples, so here and here, the density is constant. So if your density is constant, yeah, let me put that if there. So I will put if, and that if will be large. So if that density is like this, then we say that x has the uniform distribution. And in fact, there are some additional conditions. So let's go back and look here. Here we are looking at this segment starting with A and ending with B, but there are all those parts outside that segment. So what about them? Well, we told right at the start that x is inside this. Yeah, it can be only inside, and that means that it cannot be outside, and that means that outside the probability should be 0. And looking at this, so probability looks like this, and that okay, and x2 and x1 are definitely not 0 outside our segment, so our f should be 0. So that means that outside our segment density is 0. So I'll add that here, f equals 0 here and here. So it means that outside of this we should also have fx equals to 0 if x is less than a or x is more than b. And combined, those two, in fact three conditions, give us a uniform distribution. So uniform distribution is a continuous distribution of a random variable which is equally likely to have a value anywhere inside your segment. And that will never happen outside it. So that will be your uniform distribution. And now I will do one thing. I want to plot a graph. I'll put x on horizontal axis, and I will put my distribution function on vertical axis. So for uniform distribution, the density function is the same between your boundaries, between A and B. It's the same constant number. And then outside it's 0. Oh, let me change the color, because I guess that way. Okay, like this. So inside it's constant and non-zero, and outside it's constant and 0. So this is our distribution, this is our density function, and the graph itself is somewhat close to frequency polygon, which we did already see. But instead of frequencies, instead of probabilities, we have density on our vertical axis. Okay, height of that rectangle is 1 over b minus a, as we have already seen. And if you want to find the probability that your x is somewhere between x1 and x2, you take x2 minus x1, which is just the length of this segment, and multiply it by your density function. But our density function is just the height of a rectangle here. So when you calculate x2 minus x1 over b minus a, you are in fact just finding the area of this part of the graph. So it's just the area under the graph. And that's the thing to remember. So probability, I'll shorten it, I'll just use prob, but it means probability. So probability is equal to area under the graph of density. So area under the density curve. area under the density curve, and that always works. So that's the rule, that's the law. No matter what kind of density you have, area under your density curve will always give you probability. So as we said, this is only the one special case where your density is always the same. But you can also have different situations, different other distributions where your density is not constant, where it changes. So it will be different for different x's. So for example, you might have something like this. Oh, sorry. Maybe this kind of density curve. That's called Pareto distribution, by the way. So you can see that for small values of x, density is higher, and for large values of x, it's smaller, and so on. And still, if you want to find the probability that your x will be somewhere between x1 and x2, you have to find the area under the curve that is bounded by those two values of x. And how do we find the area under the curved line? So it's curvilinear trapezoid and we want to find its area. And again, if you remember your calculus, then you will know that that area is just the integral of your density function over x, starting at x1 and ending at x2. Well, most probably you did already forgot your basic calculus, which you had at the end of your high school, so either at 11th grade or at third year of a lyceum or a college. And sadly, you have no calculus here in Webster, but still, that's your probability. And don't be afraid of that, because for uniform distribution, that integral will just turn to this, because your density is constant and you are just finding the area of a rectangle. And the only other continuous distribution that we will have is the normal distribution, and the density for normal distribution looks like a bell curve. So you have something like that. And usually when you need to find the probabilities for normal distribution, you don't need to calculate that interval. You will just use ready-made tables. So at the end of most of your textbooks there is a so-called z-table, which is for areas under the normal curve, and we will look into it a bit deeper on our next lesson. But it will be that way. So in one case, instead of an integral, you just have this thing, which is easy. And in other case, instead of an integral, you will just be using your tables. But for now, let's go back to the uniform distribution for a bit. So I will restate everything here. So uniform distribution is a continuous distribution where your random variable can acquire values between some a and b, and your density function is constant. It's 1 over b minus a everywhere inside the interval, and it's 0 outside the interval. Okay, now you have already seen. Oh, by the way, you might find that uniform distribution very similar to the case of gaming dice or a coin, right? So both for a coin toss and for the gaming die, you have the same probability for each outcome, and in some sense you have the same here. You have same density for each outcome for uniform distribution. So the distribution of the outcomes of a dice roll is a discrete version of or how do you put it, of a uniform distribution. And for calculating the parameters of that distribution, so if you go to the dice roll, you have 6 different outcomes ranging from 1 up to 6, and if you want to calculate say the mean of the distribution, you will add all those outcomes starting from 1 and up to 6, and then you will divide it by 6, and you will get 3.5 for mean value, and 3.5 is just 1 plus 6 over 2. So in fact you get the same result as if you only added the boundaries and halved them, and that's the case for uniform distribution too. So mean value of a uniform distribution is just a plus b over 2. So it's just the center of the interval. And so there is no mode, right? Because you don't have any value which has more density than others. The median is just the same as your mean. It's the center of distribution. So our distribution is symmetric. And there is one more thing which I'm forgetting to do, but yeah. So variance of uniform distribution is just the length of the interval squared over 12. Okay, so if we look at our previous example, when you come to the campus somewhere between 1 p.m. and 2 p.m. randomly and uniformly, then the mean time of your coming to canvas would be 1:30, the center of your interval, and the variance would be 1 over 12 hours. So it will be 5 minutes. So you can say that on the average you come to the campus at 1:30 plus or minus 5 minutes, so to speak. Okay, so that's our uniform distribution. That's our continuous distributions, and that's our uniform distribution. Let me summarize. Let me go back to continuous distribution and summarize. So we have discrete distribution and continuous distribution. For discrete, you have separate outcomes. For continuous, it's not the case. For discrete distributions, the number of outcomes is countable, and for continuous, again, it's not the case. For discrete distributions, you have a probability for each outcome. For continuous distributions, you have probability only for intervals. And for separate outcomes, well, for the unique outcomes, you have density. So, in some sense, the density plays the same role for continuous random what do you call it? For continuous random variables. Oh, I've lost the thread, so let's do it from scratch. So the density function plays the same role for continuous random variables that the probability plays for discrete random variables. Oh, and by the way, so instead of saying density function or probability density or density every time, you can just call it PDF. So PDF is probability density function. Okay, so where you have probability for discrete events, you have PDF for continuous events. And also, we have already seen that when we have large amounts of data, the frequencies are proportional to probability, and that's the law of large numbers. Well, that's exactly the same for continuous variables too. So frequency for some interval will be proportional to probability for that interval, and frequency for one exact value will be proportional to density for that exact value. Whew, okay, so that was a lot for one day. If you have any questions, if I forgot to clarify something, or if some parts of the lesson are obscure or unclear, feel free to message me, to ask me, and don't stop until you get your explanations. And that's all. Okay, bye.